Hello and welcome back to Calculus 3. Alright, section 11.9, curvature and normal vectors. It's the end of the chapter, right? So you can think about the exam, I guess, if you want to. We are focusing on, again, curves, and we want to quantitatively describe curvature. We know that a straight line doesn't have curvature. Well, we'll define it as something as we go along. You take a piece of wire, any type of wire, and you just let it form whatever, right? So you have whatever type of wire, and you know that there are some segments that curve more than others. Now, what would that mean? If you think about in terms of the tangent lines will turn in space faster as the line progresses through your vector value function as the t progresses from, let's say, 0 to whatever number. So we know that we can describe this particular piece of wire or whatever looking at your xy z plane, taking vector r to location, and we know that that r is given as your vector valued function that has f of t, g of t, and h of t. So this vector r for space is the standard vector of all of those parametric functions as a collection, right? So far, nothing new. When you think about the vector r and its progression through the line, this position over here could be, let's say, t equals 1, and this position is t equals 2, t equals 3, right? And this parameter t could be seconds or minutes or years or whatever. Observe what's happening at each of these locations, right? The curve at t equals to 4, right, curves more, bends more than at t equals 3. Now, we know that there are tangent lines. Observe what happens with the tangent line t equals 4, and then pick a point close by. The slope of that tangent line is vastly different than at t equals to 4. Now, if you focus at t equals 3 and you just move a little bit left or right, those slopes will be pretty much the same, right? So this is the way for us to quantify curvature through Calc 3, right? We are going to take a look at the neighborhood and see how much that line, the tangent line, changed. And we know how to calculate the tangent line. So the faster it changes in the neighborhood, we can define that as larger curvature. And if the variance in the tangent line is not as much, like around t equals 3, we can draw two tangent lines that would pretty much have the same slope. In that case, there's not that much curvature in that case. So what is the curvature for the straight line? Exactly. Very good. Good answer. I know. Glad you're thinking ahead, right? So what is the formula for unit tangent vector? Who can help with that? The t hat? Oh, we should have a quiz right now. Yes.
Is it r prime of t over the magnitude of r prime of t?
Very good. So unit tangent vector is the velocity vector, right? The v of t divided by speed, which is the magnitude of the velocity. we are in mathematics obviously focusing on the formula that we use to compute things. This was the last class, right? The unit tangent vector. So this is the calculus definition. And then the meaning, right? Because remember, r is the position. It's like a path that we have. And then when you take the derivative of that path, you are getting the formula for velocity. So we can describe this particular unit tangent vector as the derivative of the path or as velocity divided by speed, which is the magnitude of the velocity. So that's the first part that we are going to need. And then we are going to use this vector to define the curvature. So here we go with the definition now. Definition of the curvature. So let r of t describe a smooth parametricized curve and then if S denotes an arc length, and t hat is the vector we just seen, which is the vector r, derivative of vector r divided by the magnitude of r, is the unit tangent vector. The curvature is given as, use k of s as the derivative of the unit tangent vector in terms of that curvature. We are not going to use this to compute things. We are going to use the different formula. You will see many of the future definitions in Calc 3. We use one concept to define the concept, right? And then we use easier formula to compute. So the formula might not have the insight into the concept, right, the one used for computation, where this one over here doesn't have much of the computational power to it. So first of all, the meaning of this, again, when they say arc length, the arc length is clearly the path, right? So the arc length could be a piece of a wire, right, that you want to observe. And the unit tangent vector gives us the direction in which the curvature is going to progress. So you guys can see that the derivative of that is going to give you, it's like a ratio, right, of the two that shows which way the line curves. Now, the manipulation that we can use here to transform this into the useful equation, right, is, as every true mathematician will say, trivial. So, right, it's on that list. Was it proof by intimidation or what was it? There was the list of 30-something different ways to do the proof. So we have k equals dt ds, and then what we do is we involve the derivative. This step is not shown in the book, but that's okay, which gives us dt over dt divided by ds dt. There we go. Much better. And this becomes, come on, 1 over velocity times the change in the tangent vector over in time. So what is the actual formula? Now we know that this is velocity, this is r prime. So we can actually, I'm going to write this as a formula because you guys are going to use, this is a theorem. The proof was given up there. So curvature formula. Oh, is this? Yeah. All right, so this is the issue that I was telling you about that the OneNote has. So some of the stuff will disappear and then you have to go back and fill it back in. So the curvature formula would be that curvature of t is equal to, and we can describe this as the derivative of the unit tangent vector divided by the r prime of t. So these are the magnitudes, and this is the formula that you would use to calculate curvature of whatever vector valued function you have. So now if you have some kind of vector valued function given to you, which describes, right, we know the helix, right, the spring spiral, for instance, has the cosine t, sine t, and then t. So this would be just a regular spiral, right, the spring helix. So you have the third-dimensional vector valued function that describes this particular helix. You can compute the curvature everywhere around this helix, and if you pin time, let's say t equals 2 seconds or whatever, you will actually find the curvature at that point. So the curvature is not necessarily a number, right? It's not number immediately. Curvature is going to be a function because the curvature is going to depend on t, and it might change, right? Because curvature doesn't have to be uniform for the entire wire. You can see there are straight parts and there are very curvy parts as I pick up this wire. So,
can you scroll up, please?
Yes. This is all gone. I'll fill it in while you guys do this example, obviously. So you have the formula, and go ahead, find r prime, then find t, then find its derivative, plug everything in, and be done. So I have to go back and fill in the stuff that disappeared. So I'll just give you the formula here, so you can work. And I'll go back and fill in the blanks again. Now these problems are a lot of calculation, obviously.
R squared, so it becomes 1, right? And t is equal to r squared equivalent of magnitude of that thing. Yeah.
That's what I thought. I started finding the derivative of this, but I thought this was wrong. I thought it was r. So we have to find the derivative of that.
Right, it's getting late. That time of t is, I don't know, you might have just miswrote it. It could be, that could be the problem.
I thought it was like, I thought you already wrote it like that, so that's why I didn't.
I'm honestly. I'm not sure. I don't know if it's right, but I'm using the screen on what magnitude of that. Yeah. As good as these two
All right, let's take a look. Since you guys already having a party, so I need to obtain r prime, which would be derivative of cosine is, very good, derivative of sine is, and we have 1. So now, to get vector t hat, we are going to divide our r prime with the magnitude of r prime. And what's the magnitude? What's the magnitude of r prime? Square root of 2. Very good. Because when you square the first and the second, you will get sine squared and cosine squared. You add those two, you get 1. And then you have this one, so 1 plus 1 is 2. So we have a square root of 2. So what do we have? We have our vector t to be negative sine t divided by root 2, cosine t divided by root 2, and then 1 over root 2. Now you can go and rationalize all of this for t, but yeah, let's just keep going. Let's keep going because we need to find t prime, and then maybe this root 2 will somehow work out later. So to find the t prime, we are going to take derivative of each one of these. So derivative of negative sine is negative cosine, still over root 2, it's a constant. And then we have a negative sine t over root 2. And then we have 0 over here because the constant and derivative of that is 0. Finally, I need to find the magnitude of this and divide it by the magnitude, well, with the speed, divided by square root of 2. So the magnitude of the t prime is going to be, and now I have to square each one of these. So as I square the first one, minus sign goes away, right, because it's squared. So we have cosine squared t divided by 2 plus sine squared t divided by 2, and then we have a 0. Here's 0. So you're all happy. Well, you know that the happiness is important to us, especially in math. Right? So we have sine squared plus cosine squared is 1. So the whole thing becomes square root of 1/2, which is 1 over root 2. And the curvature is defined as the derivative of the unit tangent vector divided by the speed. So we have 1 over root 2 divided by root 2, which is 1/2, right? Are we all agreeing on this?
Right, this is the r prime, right? But this one we put r prime on top of this one instead of just regular r, which is cosine to sine.
No, it's r prime or r prime.
It's r prime.
Okay. No, r prime, both. Remember that the tangent is the derivative, right? From Calc 1 you know tangent is the derivative. So, okay, let me... I'm just going to... Oh, this formula got a little bit crazy over here. So the tangent is the derivative, right? And then we have... So tangent is the derivative. Okay. What else? Yes.
What exactly is the curvature? Because in this situation, the curvature is constant, so...
Yes. And the reason is, when you take a spring, now you can't really use the spring from your pen, because spring in your pen is going to be densely coiled at the edges, and then it's going to look evenly coiled as it goes down, and then again another dense coil at the end. But if you take a coil, right, of the spring, just look at the middle of the spring, you see that it's kind of uniform curvature, which is the reason why it's constant for the helix. But for this wire, you are not going to have a constant curvature. It will depend on where you're measuring the curvature. So curvature is quantification of how much the line in space turns at the location, right? So curvature exactly means curvature. Like whatever you would use to describe curvature using the English language, right? It's exactly what it means here. It's not disconnected. It's just with the quantification. So in this case, it is constant because it is a constant spiral down. But if you are to, bring in any kind of excitement to it, like this, right? It's going to be a different curvature at different points because the line curves more or curves less. And this was a square root of 1 over square root of 2 divided by the root 2. Now, here. What is the curvature of the straight line? So this is a standard honors question if you are in the honors section. You have to write the parametrization for the line. So write the parametrization for the line, straight line. You should know that formula from last week. And then just run the curvature for it. What is the parametrization for the line? Anyone? Straight line. R equals what? What happened? What are the equations? 3 of them. Yeah, I'm gonna go home now.
It's constant, right? I didn't watch that. I missed it. Oh, yeah.
Oh, really?
No, not really.
So this should take about 23 seconds.
That's what I was thinking too. That's just like the point. X0, you can't like put input. Well, what are you making this for? You're also making this for? Well, I think this is just like a constant. That I feel like how the team go there. Everything's on. It's all probably going to be zero, right? No, why? Yes, like this whole system has yeah. Because I opens up 7 days before test, and exactly what's on the test. And each one you can play over 70% line. That's one extra point on the test. Yeah, but like there are 4 questions out. I didn't find them to be way harder than and you can keep only open for that 24-hour section in the morning, and then closed or gone forever. Next day, next week. Yeah. Yeah. Personally, I got like 80% as well.
But I'll try to.
Yeah, 100%.
Just the
I hope that's on my back. Yeah. It should just like have a little announcement on the page.
So you're saying I thought that isolation was just A.
Because XO, YO, ZO, they're all constant. That's not a function. That XO, that's their point.
Yeah.
That's
Yeah, makes sense. And then once you figured it out, you
Yeah, figure that out.
All right, did you all get 7?
No, I got 23.
We have like 2 more minutes.
Because that's wrong. When you stare at these things, for a long time, you make these kind of levels of derivatives in your head, and the first level of the derivative would be the 0th level, which is r, and then you have this r prime, which gets you into t, and then if you take another derivative from there, gets you into t prime. So if my r is starting at t eventually getting here, the derivative has to be 0 because it's going to go a variable constant and the derivative of constant is 0. So this is the type of analysis that you guys can take immediately to see, you know, what the end product is for the straight line. Now, as soon as you involve trig and t squared or square root of t or whatever else other than the linear stuff is going to remain, right? So to start this one, we have our r prime of t to be simply ABC, because x0, y0, those are all constants, right? And then the derivative of t is 1, so ABC on r prime, and your magnitude over here is simply a square, right, b square, c square, and you can create your unit vector t, unit tangent vector t, with vector, I'm just going to say a, b, c, all of it divided by the square root of a squared, so I'm not writing it 3 times.
That was also a question I was going to ask. You kind of get lazy with it and just leave it like that, because that's a scalar quantity.
Yes.
So.
It's okay, and the whole thing is, as you can see, it's a scalar. Well, this is a vector, but it has three numbers there. There are no variables here. It's not a function, right? It's just constant, 3 constants in a vector. And now, as soon as you hit this with the derivative to find the t prime, you get 0, 0, 0. Divided by the square root of a squared plus b squared plus c squared. And now when you find the magnitude of the 0 vector, you better get 0. So what's the curvature? Curvature everywhere, right, in terms of t, would be the 0 divided by the square root of a squared plus b squared plus c squared, which is 0. So curvature for the straight line is 0. As I said, on the exam for the honors section, the question might just say, prove that the curvature of a straight line is 0. You have to know formula, right, and then work out the argument. So that's the curvature for the straight line.
Can we actually put that one on the exam? Like this exact proof? Like,
I thought that was my job to pick.
I think I would, you know, I think it would be an easy one for you to grade. So that's all I'm thinking about. You know, I have your mindset there. So
I respect that. So thank you for thinking of me. That is very noble. I will definitely consider it. Chapter 11, definitely heavy with proofs that you can do. Great. One more concept is the principal unit normal vector. There are also some concepts that are useful for those of you going into physics and statics. So please look into the forces and then decomposing forces, and also looking into the acceleration vectors and all of the other stuff that is application of this. We're going to take a look at some of it, but clearly we can't look at all. So principal unit normal vector. Somehow the title should hint that we are looking for a vector that it's orthogonal, i.e. 90 degrees, to the tangent vector, right? So this is going to be just another layer. And a calculation for this could be easily a page of really messy algebra, because again, you have it's a third layer of the derivative, and you already seen that these guys can be very, very tricky. So unit normal vector. And the notation for this is going to be capital N with a hat. Again, hat is the unit vector. All other vectors have arrows. All right, so if you are looking for the fastest way to remember the formula, remember, zero formulas on any of the papers going into the exam that you want so much. The fastest way to remember that is when you have a curve of some kind in Calculus 1 and you pick a point, let me curve more over here, and you pick points somewhere. That point had a tangent line. Now I'm going to put the tangent line and say, okay, that's a vector t, unit tangent vector. Now remember that it was the derivative and it was perpendicular to the actual radius because this little curve piece in the neighborhood of the point is a part of the big circle that has a center somewhere. So when you stretch from that center a line to your point that you're observing, there is 90 degrees between the tangent line and that vector. So now the normal vector will be the one that is perpendicular to all of this. So it should make sense that you are expecting the same calculation to carry over. So what was the calculation for unit tangent vector? It was r prime divided by the magnitude of r prime. So normal vector, right, going into the next level of another 90 degrees to the tangent should take in the derivative of tangent vector divided by the magnitude of the tangent. This is just what I would consider as a common sense projecting the next level up. I did not talk about the concept yet, I will, but when you're looking at the formula, right, you understand that the tangent line is perpendicular to the curvature at the point. You should know that from Calculus 1. Now in Calculus 3 we learned that the tangent vectors are derivative of r divided by the magnitude of r, derivative of r. And if you take a look at these two formulas, they're identical. Except this is the next level up. So we can talk about the unit normal vector, principal unit normal vector from principle of arc length again, right? We start with the arc length, but then the formula will be this one for you to use. So maybe I should just box it here since I have it and say formula, and then go back and talk about the concept. So the definition for the principal unit normal vector will be that principal unit normal vector in the terms of the parameter as arc length, right, with the derivative of ds divided by the magnitude. Yes? So that would be which is 1 over curvature of the derivative of the unit vector. Now we can't really use, so this is the definition, and it says that your actually, let me ask, see if anyone actually got this from reading. What is the purpose of this vector? What does it do? What does it show?
Which vector?
Normal.
The normal?
Yeah. That's the curvature. Curvature shows how fast it turned. What would the normal vector show? Yes, what kind of direction? That would be the tangent vector. The tangent vector gives us the direction. Just remember the car slipping, right? You have a wet road and the car slips over here. It will go tangential to the road.
So it would be, I guess, yeah.
What kind of direction? It does show direction, but
The derivative of t over ds. Directional radial.
yeah.
The center of the circle, where if it was like, obviously it's not a circle, it's a curve, but if
Yeah.
it was a circle centered for that curve, the direction towards that center,
Away from it. Yeah.
away from the center.
So it is at the point of the curvature, it is showing the direction to move away the fastest away from the curve. You see, if you have a curve right here and you pick a point, let's say here, so you can leave this point this way, this way, this way, this way, this way. You can leave this point in so many ways. But there's only one way, which is coming out from the center through this point, going this way. And that's the normal vector. It's the one that gets you away from the line in the fastest possible way. You are not close. You see, this one is kind of close, 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 right? It stays. And this one, it's, you know, if you pick this point, right, it goes away from the curve the fastest. So if you really want to think about these things in, you know, and use them, you have to understand the concept of what it does. So when you have a curve, one more time, when you have a curve, this particular, let's say, motion for the tangent vector, this way, right, if you draw the tangent vector this way, it will show you the orientation of the curve, which way the motion happens in terms of your parametric equations, because this vector here, r, is the vector that is given as a parametric set. And we know that the parametric set has the motion one way or the other, depending on which way the t is going to progress. So the unit tangent vector is just going to give the direction on which way the curve is going to progress. And then the normal vector, which is 90 degrees to it, shows the direction in which way you can escape from the curve the fastest, right? So if you take another direction, let's say this one, and you measure 1 inch this way and you measure 1 inch this way, this 1 inch here is going to be much closer to the curve than this 1 inch here. So that's technically what's happening with these measurements. You have the formula. It's the same as the formula for the tangent vector, except everything goes up by 1. And now it's time for you to suffer and compute one of these things, which is you plugging in everything in. I just need to find something from, I'll pick something from homework so we don't stay here forever. Find the unit vector tangent t and the principal normative vector. Of course, you have to find both. How about 2D, so we're not here forever? So problem 30, here's your r of t as t squared over 2, t cubed over 3 for all t is bigger than 0. And so I'm looking for the principal unit normal vector, and since I can't have everything there at once, I'm going to put all the formulas on the board so you can grind through this. what do I need? So we have r of t, r prime of t, t hat of t. No, that's wrong. Better?
This is going down. It's changing this way, right? So, planetary motion, yeah. It points inwards. Because it's the acceleration, right? And then we have the tangential acceleration and the normal acceleration. Yeah. But then when you have I think the pendulum back. I think the pendulum back. Yeah, so that is weird. See, to me, that's the normal vector, like the isn't that like the opposite of gravity, or the force that it's exerting?
Yes, that the surface exerts as the surface exerts back on the object as the object is pushing down, and it's always perpendicular to the surface.
Yeah.
Okay. Well, this
But
is all
here,
counts.
if this is the surface and it curves this way, then the normal vector will point down.
Will point down. Which is what's that case the orbit. Actually, breaking my head. Take a look at the.
I mean, I could be wrong. I just wanted to make sure.
It's the normal component. No. This is definitely the acceleration points inwards. And the normal vector is the carrier of it, because now I'm going to do the physics application. Well, I'll fix that. Okay. Can you just stay forever? Can you?
Maybe.
So I just need to make sure you don't get accepted to any school and never get a job. Alright, okay. Done. I'll let the minions.
Alright guys, so let's take a look at this together. Please note that the formulas I wrote so far in terms of r prime and t hat and n hat are just vectors in general, and they can be done in any dimensional space, right? You can have any dimensions with this. Now, as you are again looking at these, you are going to have the path, and then the velocity, which gives you also the speed, and then you're going to have the tangential vector, which shows you the direction, and then the normal vector, which actually is going to connect to acceleration, because it's the second derivative from r. Let's quickly compute this. So what's the r prime? Anyone? T squared. Great. And what's the magnitude of r prime? So magnitude of r is when you get t squared plus t to the fourth, right? And the only thing you can do here is kick out t and have a square root of 1 plus t squared. You can't get far with this. But then that helps a lot when you compute your t hat, because your t hat now is t squared divided by t square root of 1 plus t squared, and then t cancels everywhere, so you get 1 and t divided by the square root of 1 plus t squared. Would we all agree that this is a little bit better? All right, the dreaded derivative is kicking in, right? I see some smiles. That's great. So we have t prime. First, I'm going to actually... So if I was to have the t hat, I'd leave it here, right, for the t hat. But then I need to take the derivative, so I am going to actually write this as... actually, let me use this line. Maybe I should... I'm just going to box this as the t hat answer, because the book did ask about the t hat. But now I'm going to rewrite it so it's easier to take the derivative. And that's going to be 1 plus t squared raised to the negative 1/2. Half is for the square root and the negative to bring it up in the numerator. And then, comma, t times 1 plus t squared to the negative 1/2 again. And now this one is a product rule. So that would be that. So let's take a look at the derivative. So the first one is the chain rule. So drop down negative 1/2 and then 1 plus t squared, and it's going to be to the negative, right, because minus 1, so negative 3/2 times the derivative of the inside, which is 2t. So this would be the derivative of the first, and we can quickly see that the half cancels with a 2. So that's that part. Did I mention that you're supposed to put the notebooks sideways before this problem started? No? So now we have the second second component, which is the product rule. So copy the first. And now the derivative of the second, well, we already have that piece here. So I'm just going to put as negative t times 1 plus t squared to the negative 3/2. So I have a negative to steal, and t and the whole parenthesis. So that's that. Plus, copy the second one and derivative of the first one, so that's just 1 plus t squared to the negative 1/2. And all I need to do is to clean this up. So let's see, t hat prime of t is equal to negative t divided by 1 plus t squared to the 3/2. So that's a now positive exponent because they put it in the denominator. On the second one, I have negative t squared divided by 1 plus t squared to the 3/2 plus 1 over, and I'm not going to use the square root because I can simplify this further. To get the common denominator to add these, I need to multiply numerator and denominator by 1 plus t squared. When I multiply, I will get 3/2 in denominator. No coughing, right? So we have the first one, negative t over 1 plus t squared to the 3/2. On the second one, look what I have. I have 1 times 1 plus t squared, so t squared minus t squared, that's all gone. So numerator is just 1, and denominator is 1 plus t squared to the 3/2. And you could leave it here Or you can write it as simply vector negative t1 divided by the denominator. Oh wait, we are going to find the magnitude of this. Let's just leave it here. So we have our t prime, and now let's find the magnitude. The magnitude is going to be when we square all of this stuff. So we're getting t squared divided by 1 plus t squared cubed, right? The squared killed the half. Plus 1 squared is 1 divided by 1 plus t squared cubed. And the total over here is t squared plus 1 divided by 1 plus t squared cubed, and the square root of everything. Everyone happy now? You see what happens in the next step? You have 3 of the t squared plus 1s in denominator, so one of those will cancel, and you are left with the square root of 1 over 1 plus t squared squared, which is 1 over 1 plus t squared. Come on. I know, right? After all this work, it's just 1 over 1 plus t squared. Come on, where's the emotion? There we go.
Do you need...
Yeah, we still need. Yeah. We still need.
You need like the...
Yep, exactly. So normal vector is going to take the tangent over here and divide by this guy. So I am going to have negative t over 1 plus t squared to the 3/2, comma 1 over 1 plus t squared to the 3/2, everything divided by 1 over 1 plus t squared. Now that's just going to cancel this with these guys over here, and leave half in each. So 1/2 stays in each one of these. So what I have is that the principal unit normal vector in terms of t is going to be simply negative t1 divided by the square root of 1 plus t squared. And now if I asked you to compute at 2 seconds, you plug in 2 everywhere. If I ask you for 5, you plug in 5. And that's the end of it. I hope you're not disappointed. But that's it. What good is this? All this work, other than being picky about life as we calculate. Well, let's talk physics because you love it so much, right? As you spin things, right, you create tension in a string, but this motion that you've just seen is the same as the motion of the moon around the planet. So what's happening with these orbits and things that spin and so on? When I spin an object through the string that I have, that I'm holding, you have the tension vector, which is force. It points towards my hand. So if I let go, I don't have anything heavier. But as we do experiments. As I let go, right, of this, right, you see it takes tangentially takes off that way. So at all times, as things spin, as the moon goes around the planet, the speed, the velocity, the tangential vector wants to push the object away from the orbit, away out. So orbit, Earth, Moon, tangent vector, right there, right? So it actually wants to spiral out and go out. Now, in case of the string, right, this connection is physical, right, through the string, and you have the tension of the string, which is the force which pulls. So even though this vector is pushing it outwards, the string and the force is pushing it in, and the force is acceleration times. Daniel, thank you for taking physics and remembering. So it's that acceleration that pulls back. Earlier I said it backwards. I said that the normal vector is pointing out. Its normal vector is pointing in towards the curvature. So as you have the... Oh, I practice drawing circles. You know that, right? Draw perfect circles every time. Look at that.
That's pretty good.
I know, years of practice. Michelangelo can do it this way. Partly because he's dead, but there's no contest. So if I put the heavy object in here, I really don't care which way you are going to connect the other object, whether it's going to be gravitational force between the two. Can anyone give me that formula?
Of what?
Gravitational force between the two. Yes, G. M1, M2, nice. R squared, nice. Distance squared, great. So yeah, can anyone do that for the charge?
I got that question on the test.
You got that question right on the test. Great. Can we do the charge? Oh, you're looking up on a 4. It's the same formula. K, Q1, Q2 divided by, again, separation squared. Great. It's all the same formula recycled over and over again. So I don't care which way. So it's going to be gravitational force, or is it going to be electromagnetic force that holds it, or is it going to be the string, right? So you have a tension that pulls it inside. As the tangent vector is trying to push the trajectory out, the force over here, which could be ma, and that's going to be the normal force. So in the physics book, or in the calculus book somewhere, let me just find the page. Where are the page numbers? 840 or 850. There it is. 847. Tangential and normal components of the acceleration. You can see that as one is pushing the object to go away, the other one is pulling the object to go in, and the balance of those two, you have the orbit. As soon as something is in the system, so let's say the Earth disappears, right? You wait some time, the moon will spiral out, right? Because this component of the force is gone. Good. So the acceleration is going to be the normal component times the normal vector plus acceleration on the tangential component with the tangential vector. Again, this is for your physics and later on dynamics, all right, statics too. These components, and these are just regular components of any vector that you guys have. I don't have a microphone, so right. That's it. Just go do the homework now. Bye.